Okay, so here's the next stop. This is the low energy area. Goes by many names, also the precision measurement area. So point is, instead of measuring nuclei at half the speed of light, we've stopped them and now we've diverted them into here, and we're going to be able to do two different kinds of experiments. If you look in the far back corner of the room, there's a large gray barrel with a blue light on top of it. It has a Spartan helmet on one side and a Spartan S on the other, as it should. And that barrel is called the low energy beam ion trap, or LEBIT. And that is probably the strongest magnet you will ever see, unless you look pretty hard. It is a 9.4 Tesla magnet. However, it's so well shielded you wouldn't actually notice until you have to get in exactly the right spot with a wrench, and you can notice the magnetic field. In fact, my first day here, they said, "Hey, take this wrench, feel this." Do not listen to people here when they tell you that. So, suffice to say, that barrel is extremely strong magnet, and it's a trap. It's a magnetic trap for ions. As they enter the trap, in the magnetic field, they're going to be stuck and go in a circle. They're going to orbit inside that magnetic field. The frequency of their orbit depends on how much they weigh, their mass, essentially, very precisely. So if you can measure that frequency very precisely, you get the mass. In fact, that piece of equipment can measure the mass of a nucleus to 1 part in 100 million. That is equivalent to if you sat on a jumbo jet and I weighed the whole jet, I could tell you how much change you had in your pocket. So it's really quite precise. It does an excellent job at measuring the mass of a nucleus.
It's kind of the same principle as a centrifuge, as I'm trying to put this together, right? As far as, the...
But of course, nothing's actually spinning in that except for the nucleus itself.
Right.
Yeah. People come in and they're like, "You guys have a cyclotron. Is that like the ride you get on at the fair? You go around." It's a gravitron, and it's very different. But anyway, but yeah. I mean, so it's just the frequency is equal to, I think it's like QB over m. So the charge of the particle times the magnetic field it's experiencing divided by the mass. So if you can measure that frequency very, very precisely, and we can.
Just the people who come up with the equation.
How do you measure the mass? We're getting at it in a very roundabout way.
Yeah.
It's really, really clever. Sheldon Cooper does not work here.
How quickly can it quantify that mass?
So it's, like I said, it can be done within 10 milliseconds. We did that lithium-11 experiment. So that's pretty darn impressive. Another great thing about that particular detector, it's a great magnet, it's a great detector, but it's also made with the same superconducting wire we've been talking about, and it's cooled with liquid helium. So what this means is we built it, we made a coil of superconducting wire, cooled that down to about 4 Kelvin, then we plugged it in, got current, several hundred amps of current running around that coil, then we unplugged it. It will now run for several thousand years before we have to recharge it. Because there's no resistance in the wire.
What about the helium? How often?
Well, here's the thing. So as long as you keep it cold, that is the cost, essentially. You have to keep it cold with helium, otherwise it'll warm up and become a normal conductor, and then the resistance in the wire will use up that electricity. But as long as it's cold, there's no resistance in the wire. The only reason for the electricity to be used up, that's actually consuming the energy, is when nuclei enter and get stopped and go in a little circle. Well, that's very little energy. So that will run for several thousand years. It's really the best battery you're ever going to see. As long as you keep it cold, of course.
And that begs the question, can that be applied to things like...
Well, I'd love to have that kind of battery on my phone, except I don't want liquid helium next to my ear.
But for bigger applications,
so that's the
say
thing.
in a car or something, I mean, is that consider that, or is that possible?
Well, this is the thing. What we need is superconductors that operate at higher temperatures. That's what we need. And people are working on it. If we can get room temperature superconductors, everything will change. Everything will change. And it may very well happen. I can see it happening. People are working on it. It's good stuff. Suffice to say, we wouldn't be wasting so much battery power on heat all the time. That would be a big deal. So that is one type of experiment you can do in here. There is a second low energy, high precision experiment you can do in this room. It's called BCOLA, the Beam Cooler and Laser Spectroscopy Beam Line. That's right here. There's another trap in this cage over here. And as you hold your nucleus in the trap, you can impinge a laser on it from the other side. This laser is 15 watts, extremely tunable in frequency, therefore color. And what we're trying to find out is what colors of laser light will the nucleus absorb, because that tells us what energy level transitions are allowed for that nucleus. It's the same as other quantum mechanics you might have heard of. Electrons are allowed certain energy levels. Same with the nucleus. The nucleus can have this much energy or that much, and nothing in between. So you can measure that very precisely with a laser that we have here in the building. Plus, we are shooting lasers at nuclei. This is great. I mean, I tell you, we are very much on the edge of science fiction here, and that's one of the reasons I love working here. But
Is that an animatronic in there working right now then? Yes.
oh, that'd be awesome. No, that's Scott.
Oh.
Scott stands for synthetic. No, I don't know. So anyway, yes. So this is our low energy area. That's where you can do some very precision experiments. Great place to do them. It's under construction almost all the time, which is why we don't go in. They just want us to stay out and not mess with their precision experiments.
How the heck do you hit a nuclei with a laser?
Yeah, very carefully.
Yes.
Yes. Yep. Tricky business. Okay. Any other questions here? Doing great. Okay. Let's walk around.